Hi HMS modelers, my name is Matt Fleming and I work at the Hydrologic Engineering Center, and in this video I'm going to talk about the automated subbasin and reach delineation tools in HEC-HMS. Alright, so the first thing to mention is that the delineation tools rely on the Tau DEM GIS library to define the flow direction and flow accumulation grids, and then also the stream definition and the initial delineation part of the process. And so there's a pre-existing library out there with GIS functions in it, and HMS is plugged into that GIS library. As part of the GIS delineation process, the user defines the stream threshold or the drainage area required to initiate a stream. And then once the default delineation is performed, there's tools available on the GIS menu for the modeler to modify the watershed network. And so we have a screenshot here on the right that shows the GIS menu. And so the tools that we're going to talk about in this video are Preprocess Sinks, Preprocess Drainage, Identify Streams, and then once you have the streams identified, then you can define a breakpoint, which could be the outlet of the model, or in upstream locations where you want subbasin outlets, and then finally the delineate elements or tool right here. And this menu option or tool will automatically create that default watershed or basin model. Okay, so how does this work? So the delineation process relies on what we call the 8-point pour model. And so basically what this is water is going to flow from one cell to the next based on the steepest slope. And so what the program or the GIS tools will do is the tools will evaluate each grid cell, each elevation in the grid cell, and look at the neighboring cells to determine the slope, the steepest slope from one cell to the neighboring 8. Once it identifies the steepest slope, then it's going to create what we call a flow direction grid. And so what this flow direction grid does is it indicates the direction that water moves from one cell to the next. And so we have these flow direction codes here on this figure on the left, and you can see that for a direction of 1, that means that water would flow from this cell due north or straight up to this one of its neighbors. A flow code of 2 means that it flows in this direction or this diagonal direction from this cell to the upper right cell, and so on. So you can see those different flow codes right there. Once the tools know which direction water moves, then the next step is the flow accumulation step. And so the tools can start accumulating upstream cells for each cell in the terrain network. And so we have a really simple example right here. Where my mouse is at right now, this is my elevation model or the terrain model right here. Each of the cell values represents an elevation. So for example, this upper left cell has an elevation of 78 feet. The cell right below it has an elevation of 74 feet. Perpendicular to the right, 67 feet. And the cell right next to it, to the right, has an elevation of 72 feet. So if we looked at the surrounding cells, we could see that the steepest slope is going to be this in this direction from elevation 78 to elevation 67. Okay, so if we're going to assign a flow direction code to this cell right here, the cell that has an elevation of 78, that flow direction code would be 4. So here it is right here, because water is moving from this cell down to that one right there. So you could look at a couple of other cells here. So let's look at this one right here, 74. If we looked at its neighbors here, so it has 5 neighboring cells, we would see that the direction of the steepest slope is, in this one as well, 4. So water is moving from this cell right here, 74, down to the elevation 53. Okay. So I've highlighted this cell right here, this one that has an elevation of 46. So if we look at its neighboring cells, we see these two down here. So the one right below it has an elevation of 36, but the one perpendicular and to the left has an elevation of 37. The steepest slope in this case is actually going to be from 46 to 38 because the distance from the centroid of this cell to the one right below it is actually shorter than the direction from this cell to its perpendicular neighbor. Okay, so this cell in a red text right here, the value, the flow direction value is 5 because water is flowing from elevation 46 due south to elevation 38. Okay, so this is when we have the flow direction grid right here. So all these numerical values represent a direction. We can also represent the flow direction grid with these flow arrows, right? And so these arrows correspond to each of the directions in our model over here. And once we have those directions identified, we can start accumulating upstream flow area, or the number of cells, as water is accumulating as it moves downstream. And so, for example, if we look at this cell right here in this flow accumulation grid, it has a value of 1. And what that indicates is that there's one upstream cell that flows into this one. And that's going to be this cell right here. All right. And then all these cells that have a value of 0, these represent cells that are along the watershed boundary. All right. So if you make it this far, then you really have the basis for delineating a watershed network based on this model, this approach, this automated approach. And for the stream threshold, let me jump to the next slide. So we have that flow accumulation grid that we just talked about. If we determine streams based on a threshold of at least 3 upstream grid cells, then the stream would start right here. It would flow from this cell that has the 3 to the 8, and then it would start flowing diagonally down to the right, and then out right here. This would be the outlet of our little terrain model. There would be another little tributary starting with this cell right here that has a value of 5, and then it would flow from this cell with the value of 5 due south to the cell with the value of 19. Okay, so you can start seeing the stream threshold or network if we defined a threshold of at least 3 upstream cells. So water would flow in this direction and down, and then from this direction down and then out as well. Okay, so if we define streams as those tributaries or stream segments, so we'd have one stream segment here where the confluence occurs. That's where we're going to break up our network. And so we have one segment here, we have this segment right here, and then the outlet segment right there. So 3 different stream segments. And if we defined a subbasin for each of those stream segments, that would give us one subbasin right here for this tributary. It would give us another subbasin right here for this tributary, and then this local or downstream subbasin for this downstream stream segment. So if we set our stream threshold to 3 cells, we would have 3 subbasins for this simple example. If we set the threshold to something like 19 cells, then the stream would start right here and then flow out. And so we'd really only have one subbasin defined for that scenario. All right, so let's start talking about the process for using the automated tools in HMS. Well, the first thing that you have to do is you have to create a terrain data set in the software. And currently the way that HMS manages terrain data, it is a main project component. So you're going to go to the Components menu, and you're going to open up the Terrain Data Manager. And once you open up the Terrain Data Manager, you're going to create a new terrain data set, give it a name. And then part of the process of creating a new terrain data set is you're going to choose a GeoTIFF file or an Esri grid file, an ASCII file, or other file formats, but you're going to choose that terrain file and then choose the vertical units for the terrain. HMS will take that terrain data layer and it's going to copy it and create that copy or move that copy into the terrain folder within the project directory. All right, so once the terrain data set has been added to the project, then what you would want to do is create a new basin model. And within that basin model, you can first, or I would first define the coordinate system for that basin model. So as I mentioned in a previous video, there's 3 different steps for defining the coordinate system. You can choose from a predefined system, so you can choose either the UTM or the SHG or Albers equal area projection. You could, or the other option is choose an existing projection file with well-known text. And the final option is whenever you select a terrain data set, you can choose an option to use the projection from the terrain data set as the projection for the basin model. Okay, one thing I do want to mention now is if you've already defined the projection from the basin model and it's different than the terrain layer, once you select that terrain layer for the basin model, the program is going to create a copy of the terrain and reproject it into the projection of the basin model. So you've loaded the terrain into the project, then within the basin model you've chosen the terrain data layer, and once you've hit the save button after choosing the terrain data layer, you should notice in the basin model map the terrain data set is now displayed. And then on top of that terrain data layer, you can add any other shapefile that you want to on the map layers editor so that you could view rain gauges, flow gauges, the stream network, you name it. You can plot that information on top of the terrain data layer. All right, so the first step in the process of delineating subbasins and reaches is you want to run the preprocess sinks option. And so what this option is going to do, it's going to look at the terrain layer and it's going to fill in those low spots or those sinks so that water can move across the terrain and then out of the terrain. So it's going to basically create a hydrologically corrected DEM for you. 2 of the outputs from this tool, you should see those in the map layers dialog that we have right here in this figure. The program is going to create a sink fill tool. And so the sink fill tool is what we call the hydrologically corrected DEM. That's the one that's going to be used for the subsequent steps. The other data layer that's created is a sink location raster. And what that's going to show you is it's going to show you all the low spots in the terrain and then the amount of fill that was required to fill those low spots. All right, the next step is probably the most important, the preprocess drainage step. So that's where the program is going to analyze the hydrologically corrected DEM, and it's going to create 2 additional data layers. It's going to create the flow direction data layer, so that's the direction that water is moving from one cell to the next based on the steepest slope, and then it's going to also create the flow accumulation raster, and so that basically counts the number of upstream cells for each cell in the terrain model domain. Both of those data layers are going to be added to the map layers editor, and so you can turn those on or off and you can modify the draw properties for those additional data layers. All right, so after the preprocessing steps are finished, then you can identify the stream threshold. And so this is where you're going to have to think through how dense of a network, subbasin and reach network, do you need for your watershed? Do you need lots of subbasins, and so you need to define a stream threshold that is relatively small so that you can have a lot of detail, or can you get by with a larger stream threshold and fewer subbasins and reaches? So you might have to put a little bit of thought into this, or there's an opportunity for a couple of iterations, so you can choose a stream threshold, go through the process. If you don't like it, if you need more or less of the definition, then you can go back and rerun the identified streams step. And so what you're going to notice when you run this, a new stream segment is identified for each of the confluences. So a stream is going to be created like we have right here, and then the stream meets another stream, and so we have a confluence, so basically a junction in this case. And so for each of these segments, the program, when you run the next step to delineate subbasins, you're going to have a subbasin for each of these stream segments. All right, the next step in the process is to identify the breakpoints. So you have to have at least one breakpoint and that breakpoint could represent the outlet of the watershed, the most downstream point of the basin model. You can have additional breakpoints in the model, and so those additional breakpoints would represent gauge locations or other locations where you want the model to compute flow during the simulations. One thing to note, whenever you do add these breakpoints to the model, or to the basin model, you need to make sure that the breakpoint falls on top of the identified streams layer. So at all times during this delineation process, you want to make sure that the identified streams layer is turned on. And anytime you add a breakpoint or you click to delineate a subbasin, you want to make sure you're clicking on top of a cell that's within the identified streams layer. So to add a breakpoint, what you do is you click the breakpoint creation tool in the toolbar, so it's right next to the other tools that represent the subbasin and reach and other basin model element icons. So it's this guy right here. So you click on that tool, you'd zoom into your location where you need to add that breakpoint, and then click in the basin model map on top of the identified streams raster. So that's the breakpoint. So once you've identified the breakpoints, then you can run the next step. It's called the Delineate Element step. And so you click that option from the GIS menu, and whenever you do, a pop-up editor is going to look, it's going to open, it's going to look like this. And basically what this is asking is, do you want some type of default naming convention for those subbasins, reaches, and junctions? And so you can choose the subbasin prefix, the reach prefix. Do you want junctions or not? Wherever there's reaches come into junctions, or whenever some basins come into reaches, do you want the junction prefix? And then do you want to convert those breakpoints into computation points? So you can choose those options. Once you have those chosen or defined, click the Delineate button, and the program's going to automatically create those subbasins and reaches for you.